And I have to leave for a counselor.
Okay. What time?
At 9.
9. Okay.
Watching this in right now.
Can you, yeah, can you spend 20 minutes finishing it?
Yeah,
Okay.
perfect. Thank you.
Yeah.
Yeah, I think that's all I did. So I really wanted to be. I think it's on 40. Yeah, and then I went to bed like 10. Same. It was great. Yeah. Great. Yeah, don't regret. I really regret. Like all of my it's like things I got wrong about this, where it's just like stupid. Yeah. Like now I know. It's like a place like that I do like. It's because like I wasn't there on Thursday. It was like he lectured, but like I'm not supposed to know. So that's this. Yeah. Yeah. Are you going to this? No, I'm good. Yep. Oh gosh. Yes, I don't think we have anything in the I'm gonna like run 2 weeks ago. No, I'm gonna listen. Yes, yeah, figure it out. Yeah. But realize I yes. But also it took me like all of semester and I never used them. Something, right? It's like yeah. Look at myself. That's why I don't do that. I'm so thankful, Jane, for your better. That's a month. God, now I just think the next one should be back. Yes, absolutely. Yeah.
Almost. Okay, we're going to continue with our calculator test FRQ review. You can have your calculator out. We've got through most of 1 and 2, but number 2 we left off at part C and D, and we were able to approximate the rate of change that the temperature is changing in the pond by using slope. We're able to find the average temperature by using average value theorem, and then average value theorem. Within it, we used trapezoids to approximate the area under the graph, or accumulate all the or approximation of all the temperatures added up together. And then part C, we're now going to go back and rethink A and B, but then with the calculus perspective. So let me read part C here. A student proposes that a function p given by p of t equals 20 plus 10t e to the negative t over 3 as a model for temperature of the water in the pond, time t, where t is measured in days and p of t is measured in degrees Celsius. Find p prime of 12. So now we're going to find the exact rate of change at 12, because now we have something that is not just every 3 days. Now this is supposedly every moment, not only days, but also like 1.2 days, or, any value that is that we can think of between 0 and 15. So we're going to make the calculator find the derivative for us. I mean, I guess we could do this by hand again. We could go through product rule and then plug in 12 and do that. But This is calculator section, so we're going to make the calculator do it for us. So in your calculator, you're going to go to y equals. We're going to type in that function here. Now, if you have a 36 Pro, you can just enter it directly into your Math 8, but I'll show that in a second. In your calculator, you're always going to use the variable x, even if on paper it's showing t or y or w, you're always going to use x. So let's type that in. So 20 plus 10x e, so e is second ln, and then negative x over 3. Okay, we're not going to graph this. We're going to go back to our home screen, second mode. And then you're going to, I'll leave this up on the board here, Math 8. Math 8 will get you to your derivative feature. We're going to be asking for the derivative of this function on the 12th day, the rate of change of temperature on the 12th day. So do Math 8. So now you're do d over dx. And I'm going to call this function. I don't want to type it in at this. I mean, you could, but we already have it stored under y1. So on the board there, well, yeah, there's one way is vars, y vars function y1, but most of your calculator has math prints. So if we do alpha trace, you'll see a menu with a drop-down menu, select y1. So now y1 is holding your p of t function, and we just want to find the slope or the rate of change on the 12th day. So the calculator is going to do a couple of things for us. It's going to find the derivative, and it's going to plug 12 in for us, and it's going to tell us the rate of change. So that negative 0.549, that should be related to this, right? This is not as accurate. Here on the 12th day, using our table of values, we see that the temperature is decreasing by 1/3 degrees Celsius per day. But here's the more accurate, potentially more accurate evaluation where the temperature is dropping by negative 0.5 degrees Celsius per day. But they're both referring to the same information, just one is algebraic approximation and the other is a calculus, potentially exact value. So before we would have to say that W prime of 12 is squiggly line equal to, because it was just an approximation, but now this is more accurate here. So P prime of 12 is exactly negative 0.549. But units are the same, still degrees Celsius per day. If you're using a 36 Pro here, you will do second ln. So second ln will get you to your derivative notation, and then you'll type in that function, and then you'll do x equals 12. So once this looks like the graphing calculator screen. Once the graphing calculator hits that Math 8 and derivative. Any questions? All right, part D, use the function P to find the average value. So we're going to be trying to do trying to get the same data as part B, but then potentially more accurate. Here we saw that the average temperature is 24.5 degrees, and here we should be getting something in that range as well, but just a more accurate version of average of approximation. So average value is 1 over B minus A. So essentially, we're going to be adding up all the temperatures from 0 to 15 days, and then dividing it by 15 days and see what the average temperature is. But that's right. Sorry. For part B, we made an adjustment. We just did average temperature for the first 12 days so that we don't do as many trapezoids. But yeah, this one is 15 days. but we're going to use P of t, right? The formula was f of x, but we're going to use P of t. Okay, we're going to make the calculator find this for us, and then we don't want to forget to divide by 15. So now we're going to do math 9. So math 9 is going to now be your integral, your definite integral feature. And then in 36 Pro, it'll be second integral. So second is right below that d over dx. Do you see that? So once you're there, we're basically at the same screen. It's just that with the graphing calculator, we can call the function, but your scientific calculator, I think you have to type the function in every time you want to use it. Okay, so let's go from 0 to 15. Alpha trace, select your y1, which is holding your P of t. 386, this is the sum of all the temperatures from 0 to 15 days. And we're going to divide that by 15. So it's roughly the same. I know that the day intervals are different here, but it, just by thinking about those values, that makes sense, since all our temperature values is between 20 and 31 degrees. So it makes sense that the average is somewhat close to what we gathered for 12 days using trapezoids. Any questions? Okay, let's go to page 2. Okay, so the graph consists of 3 lines and semicircles. So we have 3 line segments. We have a semicircle here. Let the function given by g of x equal the integral from -3 to x of f of t dt. Find g prime and g double prime. So let's do this. So we'll say g of x is equal to, I'm going to write g of x again just to have it in front of me here. So g of x is not the f. So this is the f graph here. But we see that g and f are not the same thing, right? Because I have to, the g function is involving the area or the integral of the f. So these functions are basically staggered in terms of their relationship with each other. So one is at a integral level of the other, and the one is at the derivative level of the other. So to make things a bit more clear here, let's find g prime. So g prime is asking for us to find the derivative of this. And the derivative of this is basically this right here. All right, so this looks messy, right? And we're asking for the derivative of an integral of f of t. And if you remember on the test that you just took, this should remind you of a theorem, right? This is second theorem, which says that, okay, I'm applying opposing operations on the same function. We know they're just going to cancel each other out. What's left is going to be the upper bound will get inserted into the variable. So f of x times the upper bound's derivative. What's x's derivative? 1. So nothing's going to change there. So basically your g prime is just going to be f of x. What that means is that this f, I know the variable looks a little bit different, but essentially the same thing. This f is basically your g prime. This is the derivative graph of g. Now, if g prime is f of x, then we can just make both go down another level, right? So what do you think G double prime would be then? If G prime becomes G double prime, then F would become what? F prime. Yep. So they're basically they're at a staggered relationship with each other. So F and G are off by one derivative. Right. So now part B, find G of 0. So G of 0, we have all of our definitions here. So let's just say see what G of 0 is asking for. G of 0 is definite integral from -3 to 0 of f of t dt. Because my upper bound is now replaced with the x value that we found, what that they're asking for, which is 0. So the definite integral from -3 to 0 of f of t dt. So we're going to be using the graph to find the displacement involving area under the curve. Now, this part is important because a lot of you may be finding areas of regions that is not part of the diagram. So what's important is that we know what we're working on, because if you're trying to find shapes that are not defined, then that is going to throw all your answers off. The only region that we care about is between the graph and the x-axis. So let's do that first. Let's just shade in what we see between the graph and the x-axis. And that way we can just remind ourselves that we're only looking at those regions, even if you see rectangles and different shapes outside of that region. So this is a good first step for any time that you're having to use geometry to find a region. Just lightly shade in, and then you can find the area later. Okay. You may see triangles above and below. You may see all these different shapes, but if it's outside of the shaded region, then it's not part of our problem. Okay, so we're looking at the region from -3 to 0. So from -3 to 0. So we're looking at this region here. Okay, we're going to actually need all of these regions down the road. So I'm just going to go ahead and find the areas of each, and then keep in mind that this is displacement. So above the x-axis is positive slope, below the x-axis is negative slope. So here, this is a triangle here, 1/2 base times height, 1/2 1 times -2, which is -1. From -3 to -4, sorry, -3 to -2. My bad, found it wrong. -4 to -3. -2, this -1. This region is also a triangle, 1/2 base times height, 1. Here, between -3 and 0, this is basically a trapezoid, but we can always avoid trapezoids. If you don't want to do areas of trapezoids, just break it up into an easier shape. Here, we can think of it as a triangle sitting on top of a rectangle. So maybe it's just easier to find the areas that way. The triangle on top, 1/2 base times height, is 1.5. The rectangle, base times height, is just 3. Both above the x-axis, so they're both positive. Now, these little regions are not by itself geometric shapes, but is there something that we can do to get the areas of these using geometric area formulas that we know? Okay, so we got to involve two shapes, right? So we take a rectangle and we subtract what out of that? Semicircle. Yeah. So it's a rectangle minus a semicircle, and then if we were to take a rectangle and subtract out the semicircle, then what we're left are those two little curved regions. So Rectangle is width times height, which is 2. 2 times 1, which is 2. Semicircle is 1/2 pi r squared, so 1/2 pi 1 squared. So this region is 2 minus pi over 2. Here we see a triangle above the x-axis. That's 1/2 base times height. That's a positive 1/2. And then here, below the x-axis, triangle negative 1/2. Right now, we don't need all these values because it's only asking from -3 to 0. But when we get to parts D and E, or especially part D, we're going to have to come back and involve a lot of these other numbers. So again, above the x-axis, positive displacement. Below the x-axis, negative displacement. Okay, so from -3 to 0, now we have all the numbers in front of us. Let's just add them up. That's just going to be 3 plus 1.5, which is 4.5. G prime of 0, G prime of 0. G prime of 0 is equal to, let's see how we defined it as f of 0. So what's f of 0? Remember, this is the f graph here. What's f of 0? One, yeah. We're simply looking for the order pair. No longer are we asking for the area under the graph. This is simply asking for the y value on the f graph. F of 0 equals 1. Okay, G prime of -1. That's the last thing that they're asking for. G prime of -1. The definition here is f prime of x. So G prime of -1 will be f prime of -1. So what's f prime of -1 asking for? Well, first off, f of -1 is over here. What is it asking for? F prime of -1. Asking for the what at this point? The slope. Now, this is a nice straight line here, right? We can just do rise over run. So we know that we can just identify 2 points along that line segment and just do slope. So we can just start on the point on left, down 1 over 3. So -1/3. So when you have these staggered relationships and there's a graph involved, you're either doing one of 3 things. You're either involving the area, involving just simply the order pair on the graph, or involving the slope. So okay, this is a very popular type of true response question on the AP exam. So that's why I wanted to have this portion, have this FRQ test, so that you can kind of see at least 3 of the very common type of true response questions. And when we get to AP review, the hope is that, okay, by then you would feel like you've seen some of them, and then we're just going to continue to the practice once we get into March, April, and May. Okay, part C. Find all the values of x on the open interval where G attains a relative max. So this kind of goes back to first semester a bit, because we're asking for relative max and we're asking about the G graph. Now, this is not the G graph. This is the F graph. But the relationship is that this F is G prime, so this is not the G graph, but this is the G prime graph. And if we're looking at the derivative graph, let's think about first semester here. We have to interpret what we're looking at in terms of how to translate a derivative graph into a function graph. So if you remember from first semester, we know that now the y-axis, if it's a derivative graph, the y-axis represents the slope of the original graph, not the location. So we like to label accordingly here. So above and below the x-axis, remember, above the x-axis means where my original graph is going to be experiencing a positive slope. Below the x-axis is where my original graph is experiencing a negative slope. On the x-axis is where my graph is experiencing slope 0. So we're going to create a slope sign line, a G prime slope sign line. We'll label -5 to 4 because those are our endpoints. Now, if this is the derivative graph, what critical points, how do we find critical points? Where do we look? X-intercept, yep. So there's an x-intercept at -4. There's an x-intercept at 1. And there's an x-intercept at 3. And now we simply want to look, is our graph above or below the x-axis? So between -5 and -4, above or below the x-axis? Below. So that's going to translate to a down arrow, which is a negative slope. Between -4 and 1, is our G prime graph above or below the x-axis? Above. Right? Don't look at whether the graph is rising or falling. Just simply look, is it above or below? It is above, so we know that our original G graph is going to be rising. And then between 1 and 3, still what? Still above. Okay. Between 3 and 4, now it's below. So now the arrows are giving us a better picture as to how our actual G graph is moving. It's falling to a relative min at 4, at -4. It's rising to some y value of 1. It's going to flatten out. It's going to continue rising. And then at 3, what's G graph going to experience? Relative max. Yep. So that's what we're looking for, right? Relative max. So we can say relative max at x equals 3 because G prime changes from positive to negative. Okay, part D, find the absolute minimum. Anytime we see the word absolute, that's extreme value, right? So this is applying EVT here. So this is kind of first semester meshing with second semester here. Extreme value theorem says, if I want to find the absolute max, absolute min, I have to consider endpoints and critical points. And if I want to find critical points and endpoints, I'm just needing to pick off of my G prime sign line. So I just have to test those points. We have a definition that tells us how to reach these different y values on the G graph, and that's what that definition is there. But let's identify the endpoints and critical points. So we definitely need to test G of -5 because that's an endpoint. We definitely need to test G of 4. That's an endpoint. We're trying to find the absolute minimum. So what other critical point should we include? What's a candidate for an absolute minimum? And we're just looking at these numbers here. -4. Okay. Should we worry about 1? Because 1 is just the graph flattening out, right? If it flattens out and continues moving up, it's a critical point, but there's no chance that this could ever be a relative max, relative min. What about 3? Could 3 end up being the lowest point on the graph? No, right? So this is a relative. Now, if you want to test 3, it wouldn't be wrong. You're just doing additional work that you don't have to. Now, if the problem says find the absolute max and absolute min, then you want to include 3 because that relative max could end up being one of your answers. But if it's only asking for absolute minimum, you only need to test your endpoints and then any relative mins. That's it. Okay. Again, it's not wrong if you want to test more points, but we want to try to avoid additional work that's not going to help us get to our solution. Okay, so we only have 3 points to worry about: endpoints and a valid critical point, in this case, a relative minimum. So each of them gets plugged into our definition that connects f and g together. So g of -5 is simply the definite integral from -3 to -5 of f of t dt. Now, initially, you're just going to make the substitution whatever the rule tells you. Sometimes the bound that's a variable could be the upper bound. Sometimes it could be the lower bound. So you're just going to follow whatever the rule says. Don't make any changes to the rule. Okay, so now that you have what you're looking for in front of you, now we can look at the bounds and say, okay, am I reading from left to right? Because if not, we can adjust it and make it more straightforward. So what do you see here? Are the bounds in order for us to easily read it? This is backwards, right? So this is backwards. That means everything we read, we have to think of the opposite sign, and I feel like that's harder to do. So why don't we just read from left to right, and that way everything is just straightforward. If I want to flip the bounds, though, what adjustment do we have to make? Negative. Okay. So we're going to add up the areas that we see in our graph, but then after we get our answer, we have to make sure we negate that so that we're adjusting to what the problem initially had. So we'll do this piece first. So from -5 to -3, what do these numbers add up to be? -1 plus 1, 0. So here, in this case, it doesn't really matter. -0 is still going to be 0. So, but we did make sure that if there was a number here, we were ready to change that sign. Okay, next up, g of -4. So again, we follow what the rule says, -3 to -4. All right, are these bounds in order? No, let's flip them, okay? Force a negative outside. Let's do this piece first, and then we can pull the negative in front. So -4 to -3, what is that? Just a what? 1. So 1 with a negative in front would be -1. So we have that down. Last piece, g of 4. So -3 to 4, f of t dt. Again, we're just following what the definition says. And then we can take a step back and ask, do we need to make adjustments? Is this okay? Yes. So now we're going to add up basically most everything that we see in front of us. We've already found all the regions here. So from -3 to 4. So well, 1.5 plus 3 plus 2 minus pi over 2 plus 1/2 minus 1/2. So 3 plus 2 is 5. 5 plus 5.5 is 6.5. 1/2 minus 1/2 goes away. And there's a minus pi over 2. Now, this is a calculator section, but on the AP exam, this could end up being a non-calculator section. How can I get an approximation of this number without worrying about the exact value for pi? We can just substitute. What's an easy number that we can substitute for pi just for approximation purposes? 3, right? 3.14 is close enough to 3. It's enough for us to make an approximation. So 6.5 minus 3 over 2 is around what? 6.5 minus 1.5 is around 5. It's not exact, but it's enough for us to compare and know what's the largest and smallest. All right. So if you ever see pi and it's part of a non-calculator section and it stresses you out, we're like, oh, how do I subtract something with 3.14? Just think 3, right? 3 is good enough if you're just doing approximation purposes. You don't have to worry about trying to get that decimal, adding a decimal value when all you're doing is just approximating. So just put a 3 in for that pi. Okay, so we're asking for absolute minimum. So between these 3 numbers, what's the lowest that we see? What's the lowest y value? -1. That's our absolute min. So absolute minimum value is negative. Now, on the AP exam, they would say justify your answer. Normally, if it was like mean value theorem or Rolle's theorem, you would have to like provide like a potentially a sentence or conditions, or if it's IVT, you have to write all the sentence out. But with extreme value theorem, you only have to show your work. So if you are showing that you are testing your correct candidates, that is your justification. You don't have to say as many of your statements. Okay, part E. Find all the values on the open interval in which the graph of G has a point of inflection. So point of inflection is talking about which derivative? Second derivative, right? From first semester, second derivative. So if you're looking at the derivative graph, you remember how to find the points of inflection off of the derivative graph? Look for the what? Max and mins, right? The peaks and valleys. So the highest, the basically the hills and the valleys of the graph. So -3 is critical point. So is 1, and so is 2. So we're relying on first semester knowledge here with our G double prime sign line. So -3. Oh, why is 0 not a critical point? I'm sorry. Well, we're talking about peaks and valleys, though. Yeah, you're right. It's not a critical point in terms of the F prime, G prime sign line. But remember, for G double prime, we're looking for peaks and valleys, and -3 is a peak, 1 is a valley, 2 is a peak. But is 0 a peak or a valley? It's not, right? But it kind of looks like it because it's a sharp point. But there has to be a change in slope in order for it to be a peak or valley, right? This is decreasing and a sharp point, and it continues to decrease. So it's not considered. This is not considered a relative max, relative min. So I just want to point that out because some students feel like that should be because it's a sharp point, but not all sharp points is going to be a max or min. So it's only -3, 1, and 2. And if you remember, how do we read concavity based off of the first derivative graph? We look at the what? Slope. So positive slope means what? Concave up. Negative slope means concave down. Positive slope means concave up. Negative slope means concave down. So it's going to keep alternating between concave up and concave down. And we can therefore conclude that all these critical points are points of inflections because they all have a change in sign. Page 3 is more of the same. We can come back to that. Let's do a particle motion problem. Page 6. All right, an object moves along the horizontal line, v of t. Velocity is given as meters per second from 0 to 4. We're going to round our answers to 3 decimal places. So let's graph this function here. This is our velocity function. Again, if you see the variable t, you're only going to use x. Okay, we're not going to use t in our calculator. So in your calculator, we're going to type in 4 sine of x squared minus 2x plus 2 under y1. They said here to adjust the windows here, but we can, hopefully you guys are pretty comfortable with adjusting your windows. Hopefully you guys did some of that in AP pre-calc. But here the suggested window is from -1 to 5. So your x min, x max from -1 to 5. And then your y min, y max from -6 to 6. So this is the velocity graph that we see in front of us. So part A says, find the time when the object is motionless. So this is the velocity graph, which means above the x-axis is positive velocity, below the x-axis is negative velocity. So if we want to find velocity 0, we're simply looking for the what? Where on this velocity graph would the object be motionless? Or where would you look if you're trying to find where the velocity is equal to 0? Would you look below the x-axis? Would you look above the x-axis? Would you look on the x-axis? Yeah, x-intercepts, right? So your x-intercepts would be 0, right? So basically we can count potentially how many zeros there are. And then we can also use our feature. We have second trace 0 to help us find those x-intercepts for us. Okay, so try that. So I'm picking a point to the left of my first x-intercept, hit enter. I'm picking a point to the right of my x-intercept, hit enter a third time, and I get a decimal value of 2.463. We know that it's basically just representing a really, really small number, basically close to 0. So my first x-intercept, 2.463. I'm potentially doing a little bit more than I need to. It's only asking for times when the object is motionless, but I'm going to go ahead and just place them onto my sign line. It's going to be helpful down the road. Second trace, 0. I'll pick a point to the left of my x-intercept, hit enter. Pick a point to the right, hit enter. 3.29. 9. And I see one more before the 4 hits 3.903. So I'm just creating my sign line here. I can clearly see from 0 to 2.463, all this is above the x-axis. So I'm experiencing positive velocity. And then between the next two x-intercepts, it's below the x-axis, then above, and then below. So we only have 3 times when the object is motionless, because these are when velocity is 0. So t equals 2.463. 3.299, 3.903, because v of t is equal to 0. When does the object change direction? So we create the sign line here to make it easier, where all these have sign changes. So the same answers, but the reasoning is because v of t changes signs. Part C, find the velocity of the object at t equals 3 seconds. We have our velocity function stored under y1, so I can just put that directly in. There's no need for derivative. We're already at the velocity level. So if you go to alpha trace, I'm going to call y1, since y1 is holding my, again, you're at the home screen. At the home screen, do y1, and then parentheses 3. This is already the velocity function. We just want to plug 3 directly into this sine curve here. Meters per second is our units of measure. Find the acceleration. Acceleration is the what of velocity? Derivative. So we have a derivative feature, right? Math 8, we have that n derivative feature. We can use that to help us avoid having to work the derivative by hand. Just make the calculator do it for us. So math 8, d over dx, alpha trace. We already have our velocity function stored under y1. Now we just want to make the calculator tell us the derivative at 3. What's a unit of measure for acceleration if velocity is meters per second? Yeah, meters per second, which reduced to meters per second squared. Part E, this is the first semester topic here. Is the object's speed increasing or decreasing? Increasing, decreasing speed. How do we determine increasing, decreasing speed? Do you remember? What do we do? Compare what? Signs of velocity and acceleration. What do you notice about the signs here? Different. If they're different, then my speed is what? Increasing or decreasing? Decreasing, yeah. What if these are both negative? Increasing, yeah. So if the signs are the same, increasing speed. If the signs are different, decreasing speed. Okay, displacements is just the definite integral. Okay. So really, it's just as straightforward as that of v of t dt. No absolute value. We don't want to add any number to it. It is just straightforward as that. Math 9 from 0 to 4. Alpha trace, y1. Yes. See it. So this tells us that even with all the forwards and backward motion that this object is going to create or is going to go through between 0 and 4 seconds, this object is going to end up 7.7 units to the right of where he started, despite his going forwards and backwards. Part G, find the total distance. Total distance looks virtually the same with total displacement. It just needs absolute value around the v of t. So I'm going to be looking for your integral notation on the test. So I want to see your setup as well as your answer. I want to see these setups. Okay, so you'll do math 9 from 0 to 4. There's the absolute value feature. Absolute value notation is math number ABS on the board there. Math number ABS, and you're only putting the absolute value around the velocity function, not around the entire integral. So think of total distance as if someone was walking forwards and backwards, that he's always counting his steps. Despite him changing direction, he's still keeping a positive counter in his head. So here, even though he only had a net gain of 7 units, he took 12 steps because he's going backwards and forwards in that time interval. So total distance is, if there's a change in direction, your total distance is always going to be larger than your displacement. Don't worry about part H and I, can cross that out. Okay, final thing I want to go over here is part J. Part J here. Given x of 0 equals 2, find x of 4. This is similar to displacement, except this wants to know where is the object located after it's finished all of its movement. So the formula we use is final position is equal to the initial position plus displacement. It's a rearranging of the first theorem. So x of b is equal to x of a plus the integral from a to b of v of t. So this displacement is used, but it's including a starting location. So if I want to find x of 4, I'm going to start off at x of 0 because that's what they give me, my anchor point, and I just have to figure out how much progress have I made during that time, and then add it to where I started. So x of 0 is 2. 0 to 4, we can plug in the calculator, but in this case, we already have it from before, so 7.753. So this tells us that the object is going to start off at 2 on the x-axis. Over the 4-second period, it's going to travel 7 units to the right. And where's he going to end up at 4 seconds? He's going to end up at 9.753 on the x-axis because he started at 2 and he moved over 7. Okay. We need to start the next unit tomorrow, but we basically have seen these 3 well, there's one more FRQ, which is Riemann sums, which I think you'll find pretty easy. But over the next 3 days, we'll continue to review for your test. It's just that we also need to start the next unit. But your tests on Friday will just be 3 free response questions, very similar to this particle motion to derivative graph, and we'll see a Riemann sums. All right, come get your phones. No homework tonight. Let's just pick up tomorrow.